Hello and welcome to the fourth lecture on the binomial theorem. Last time we saw a few applications of the binomial theorem by working out a few examples. In this lecture we will continue working out a few more examples of the applications of the binomial theorem. So recall once again the binomial theorem is given as above. So this time we will look at a few more examples as I mentioned, and the first example is find the coefficient of the term independent of x in 3x squared by 2 minus 1 by 3x whole power 9. So once again, to solve such a kind of problem, you want to first write out the general term in the binomial expansion of the term given to you. And so a general term is given as 9cr 3x squared by 2 whole power 9 minus r minus 1 by 3x power r. So again you want to form x power 0 from a general term, and so you would want the powers of x to cancel out and give you x power 0. So notice that the power of x in this term is nothing but, in the first term is nothing but x squared power 9 minus r, and the power of x in the second term is nothing but x power minus r. So you want this to give you x power 0. So you just compare the exponents. So you have 2 times 9 minus r equals 0, and this gives you r equals 6. So the term which corresponds to x power 0 is the 7th term in the binomial expansion, which corresponds to r equals 6. And so we would have the coefficient of x power 0 is given by 9c6 3 by 2 power 9 minus 6, which is 3, and minus 1 by 3 power 6. Note that I'm ignoring the x terms in the general term because the powers of x cancel out as we set r equals 6. And so this evaluates to 9c6 times 3 power 3 divided by 2 power 3 times 1 by 3 power 6, which is nothing but 9c6 divided by 2 cube times 3 cube, and you can evaluate this result, which comes out to be 7 over 18. So this is the coefficient of the term independent of x in the expansion of 3x squared by 2 minus 1 by 3x whole power 9. Let's look at a second example. This example asks you to find the number of terms that are not identically 0 in the expansion of square root of x plus square root of y whole power 10 plus square root of x minus square root of y whole power 10. So before starting off on this example, the first thing you've got to note is that you've got to decide is that whether the square root of x and the square root of y have anything special to do with the problem, or you can just replace these by x and y without loss of generality. And for this example, it turns out that the square root of x and square root of y are just artifacts which are there to probably confuse you, and so it doesn't really matter. You could have any other two terms here and the result would still be the same. And to notice that, you just write out x plus y whole power n plus x minus y whole power n, and consider the expansion of this term. So in one of our previous lectures, we wrote out what this expansion gives us, and that is nothing but 2 times nc0 x power n y power 0 plus nc2 x power n minus 2 y square, and so on. So notice that only alternate terms survive and the other terms get cancelled out, since you have an x minus y power n here. And so you could just replace x by square root of x and y by square root of y in this expansion, and you would get an equivalent result for this particular term. And so for n equals 10, only the terms with the coefficients uh, 2 times nc0, where n is 10 now, so we can just write 2 times 10c0, 2 times 10c2, and so on till 2 times 10c10. Only these terms survive. And so this gives us a total of 6 terms that are not identically 0. So once again, to reiterate, notice that square root of x and square root of y have nothing special to do with this problem. You could as well replace them by x and y, which is what we did, and we just noticed that the alternate terms cancel out in x plus y power n plus x minus y power n, and so we only have 6 terms which survive in the expansion for this particular case. So a third example that we look at is the following, which says compute the numerically greatest term in 2 plus 3x whole power 9 for x equals 3 by 2. So whenever you're asked to compute the numerically greatest term in such a general expansion, the first step would always be to re-express it in terms of 1 plus x whole power n, to re-express your general term in this form. So for this case, we would have 2 times 1 plus 3x by 2 whole power 9. So this is again re-expressed in this form, and you can just take the 2 out of the term, and that will give you 2 power 9 times 1 plus 3x by 2 whole power 9. So the numerically greatest term in this expansion is the same as the numerically greatest term in this expansion, and we just need to consider 1 plus 3x by 2 whole power 9 to find the numerically greatest term. So a result which we shall not prove in this lecture, but which you can take for granted, is as follows. To compute the numerically greatest term in 1 plus x the whole power n, you just consider the ratio of the r plus 1 term over the r term, which is nothing but NCR x power n minus r over, or equivalently you could write it as NCR x power r, and in the denominator you would have NC r minus 1 x power r minus 1. So you just find the ratio of these two terms and you suppose that this ratio is less than or equal to 1. So you find the r for which this ratio becomes less than or equal to 1, and that r gives you an indication of the numerically greatest term in the sequence. So since we've re-expressed our general term in the form of 1 plus x whole power n, we would now have to just compute this ratio and enforce that it is less than or equal to 1 and find the corresponding r to find the numerically greatest term in the expansion. So for us, tr plus 1 over tr is, so let's just ignore the 2 power 9 for now. We just concentrate on 1 plus 3x by 2 whole power 9, and this gives us 9cr times 3x by 2 whole power r. The denominator gives us 9cr minus 1 3x by 2 whole power r minus 1. So if you expand the numerator and the denominator, you would get tr plus 1 by tr is 9 factorial divided by 9 minus r factorial times r factorial, and the denominator is going to give you 9 factorial divided by 9 minus r plus 1 factorial times r minus 1 factorial, and you'd have a residual 3x by 2 term in the numerator. So you can plug in x is 3 by 2 as well, and you have tr plus 1 by tr upon simplification to give you 9 minus r plus 1 divided by r times 9 by 4. So you want to suppose that this is less than or equal to 1 to find the r which corresponds to the numerically greatest term, and so this will give you 90 minus 9r is less than or equal to 4r, which gives you r is greater than or equal to 90 by 13, if I've done my calculations correctly. So notice that r is not an integer. So for r greater than or equal to 90 by 13, you have tr plus 1 is less than or equal to tr, and since r is not an integer, we round down r, so we have the floor of r giving you 6. So you check for t6 to be greater than or equal to t7, and in this case we have, sorry, you check for t7 being greater than or equal to t8. So you have t6 in this case to be equal to 9c5 times 9 by 4 power 5, and you have t7 giving you 9c6 times 9 by 4 power 6, and you have t8 giving you 9c7 times 9 by 4 power 7. So to check the relative values of these three terms, notice that T7 over T6 is nothing but 9C6 over 9C5 times 9 by 4, and this gives you, if you use this result which we had below, which we had above, sorry, you would get, just plug in, just plug this in here, and you would get 9 factorial divided by 3 factorial times 6 factorial divided by 9 factorial divided by 4 factorial times 5 factorial into 9 by 4, and you can cancel things out. Which gives you 9 by 6. So T7 is greater than T6. Similarly, you can verify that T7 is also greater than T8, and so in this particular case, we have T7 to be corresponding to the numerically greatest term, and so this term is the numerically greatest term in the expansion 2 plus 3x whole power 9 for x equals 3 by 2. That's it for this lecture. I hope you enjoyed watching this lecture, and in the next lecture we will look at some identities based on the binomial theorem. Thank you.